Today we have a talk of Professor Andrey Pilipenko about stochastic differential equation for low-dimensional Bessel processes. Please, Andrey.
Thank you. So this is my joint work with Yulia Mishura and Anton Yurchenko-Titarenko. One, they emailed me and asked about stochastic differential equations for Cox-Ingersoll-Ross process. They studied this process for a long time, and I studied some Bessel processes and stochastic differential equations with singularities, and we discovered that some of my approach is very useful for solution of their problem. So what is the Bessel process and what is the Cox-Ingersoll process and squared Bessel process? The definition is the following. It is easier to start from square of delta dimensional Bessel process, and this is a solution to a stochastic differential equations of the form 2 square root of x of t dw of t plus delta dt, where delta is non-negative parameter. And you see, diffusion coefficient is Hölder continuous function with parameter 1/2. And it is well known if you have this regularity, well, and drift coefficient is Lipschitz, then there exists a unique strong solution to this equation. Moreover, if initial starting point is non-negative, then using some comparison theorems, it can be proved that x of t is then x of t is non-negative too. So we may write equation without absolute value here. And the Bessel process is just square root of quadratic. Probably this is the easiest way to introduce the Bessel process. So why is a Bessel process with dimension delta?
I'm sorry, this
yes.
delta is the same as the drift, or you use delta?
Yes.
Dimension.
This dimension means delta in drift. Yes.
Okay, but everything happens in some RD, so there is also.
Yes, if you consider RD and if you consider multi-dimensional Brownian motion in RD, so modulus of Wiener process is d-dimensional Bessel process.
Okay, I see. Thank you.
But you can write down Ito formula, then apply some theorems about continuous martingales and prove that absolute value of these satisfies some equation. I will write it a little bit later, where delta is d. But you can write this equation for any d, say square root of 2. Well, it is well known that if delta is greater than 2, then y and x are transient processes. if delta is greater than 1, then the process y and x never hit 0 if initial starting point is positive. The process does not hit 0. And if delta is 1, then yt is just reflected Brownian motion. Is reflected Brownian motion. And if delta is between 0 and 1, then y of t is not a semi-martingale. Is not a semi-martingale. Actually, delta belongs to 0, 1 if and only if y is not a semi-martingale, and the process does not hit 0 if and only if delta is greater than 1. And yes,
can I ask a question about the last one property? We can say the problem arises only at 0.
Yes,
yeah?
exactly. So this process hits 0, but is not a semi-martingale. And we will apply Ito formula, and we can write down stochastic differential equation for y up to this moment.
Yes,
and the question is what happens later. And today I would like to show you the very simple proof of the form of SDE for y, and very simple proof. Actually, the equation was written by Bertoine in 19. So equation for y was given by Bertoine
for arbitrary delta.
Yeah, and this case, this is not trivial problem. For delta greater 1, this is obvious.
I have one question. It remains one case if delta equals 0.
Yes, and if yes, okay, yes, if delta is 0, then y of t hits 0 and then stay at 0 forever. So 0 is absorbing point. Then 0 is absorbing. So the process hits 0 with probability 1 and then stay at 0 forever. And actually, 0 is a solution of if delta is 0, then 0 is solution to this equation with 0 initial condition. Okay, and now let me write down Ito formula, some equations, some intuition, and then the main result, and then the proof. Well, today I will consider SDE of the form a dt plus sigma square root of x of t dw of t. Well, and Cox-Ingersoll Ross process is the process when you subtract here minus b of x of t, and everything can be done for this process, but the idea for Bessel and for Cox-Ingersoll Ross process are the same, and all calculations are the same. So I will not write this additional term. And if you write Ito formula, then up to the moment of hitting 0, you will see that y is a solution to the following SDE. Y of t is equal to sigma over 2 dw of t plus then I minus sigma squared over 4 divided by 2 y of t dt. And you see this function has really a problem at 0. It is discontinuous. It converges to infinity as y approaches to 0. So there may be a problem. So t is less than t from 0 to sigma 0, where sigma 0 is the moment of hitting 0. And well, let me write down this equation in integral form. Initial point plus sigma over 2 Brownian motion plus integral from 0 to t. Well, assume that there is a solution and everything is defined. A minus sigma squared over 4 y of s ds. And well, it is known that the process y has a local time. And we can represent the integral. Well, we may try to represent this integral using the local time in the following form, like integral from 0 to infinity, the function 1 over y, and then local time of y. We know that the local time exists. And local time, I consider local time as visitation, as a density of visitation measure. And then t y dy. And it appears that if a is small, I forget here to write 2, if a is small, and today I will consider the most interesting case when a is positive and less than sigma squared over 4, that this integral diverges. However, it can be proved that this local time, it has some nice asymptotics in a neighborhood of 0. And it can be represented as a function y to the power 4a over sigma squared minus 1 times some function, continuous function a of ty. This function is continuous. We will discuss this representation a little bit later and why this function L small is continuous in t and y. And now the result. The process y of t is a solution to the following stochastic differential equation. Y of t is y0 plus sigma over 2 Brownian motion plus a minus sigma squared over 2 over 4 divided by 2 times the principal value, integral of principal value at 0 of this integral ds over y of s, where principal value of this integral is equal to regularization of this integral at 0, and regularization has the following form. Integral from 0 to infinity y to the power 4a over sigma squared minus 2. So this y divided by this y times LTy, but we have to subtract LT0, the local time at 0, dy. And as I told you, it can be proved that there is a modification of this L, which is continuous in t and y, and is continuous at 0 too. So there is a version of this function which is continuous at 0. So if you subtract this term, then this integral is absolutely convergent. It appears that this integral is absolutely convergent, and the Bessel process is a solution to this equation. And now, one question: is it a weak solution or a strong solution? And the answer is strong. By the way, x is a strong solution to this equation. X is a function of w, and y is a function of w, of a linear process. So y satisfies, so y is a strong solution of this equation. Well, this result was proved by Bertone, but his proof is very different from ours, and actually is complicated. Yes?
Can I ask you about such suggestion? Maybe we can get the statement about the existence of the local time for y, just using maybe a change of variables using local time for x.
I will tell about this, and we will not use x, but a Brownian motion. So
Yeah, okay.
properties of local time will be clear, even Hölder continuity at 0.
And about regularization, you use well-known idea to regularize the divergent integral or not regular function which you want to be generalized, a good generalized function. So in this way, I can imagine that when we don't reach 0, everything will be
If you don't hit 0, then there is no problem at all. And you will not have this term.
Exactly.
And local time at 0 will be 0, just 0. Well, but this formula is not mine. This formula is by Bertone.
Yeah. Okay.
Okay. Now let us start the proof. At first, let us consider the process x plus x of t plus epsilon. So let me write that y of t is square root of x of t, and we have a problem at 0. So we cannot apply Ito formula because square root is not twice continuously differentiable, and 0 is a bad point. But the process x plus epsilon is greater than or equal to epsilon. So you can apply Ito formula for the process y epsilon, which is equal to square root of x of t plus epsilon. So there is no problems at all. And if you write down the equation, then you will see that y epsilon of t is equal to, well, initial starting point plus epsilon square root plus, let me write, plus sigma over 2 integral of square root of x of s over square root of x of s plus epsilon. Pardon me? I don't hear the question.
No questions here.
No question. Okay, and plus 1/2 integral from 0 to t a over square root of x of s plus epsilon minus sigma squared over 4 x of s square root of x of s plus epsilon. Oh, no, excuse me. Denominator is to the power 3 over 2 ds. And now we know that now let us send epsilon to 0. Then this converges to square root of x of t. So left-hand side converges to Bessel process. This converges to square root of x. Well, and convergence is almost sure convergence. Well, not almost sure, for all omega. Now, this process converges to 1 for almost all omega and almost all s with respect to the big measure. So if x of s is not 0, then this converges to 1. If x of s is 0, then this is just 0. But it is known that Bessel process and squared Bessel process spend 0 time at 0 with probability 1. So almost surely this process converges to 1, and hence this integral converges in L2 and even more uniformly in probability to integral of 1 dw of s, so to Brownian motion, to Wiener process. So the second term converges to sigma times Brownian motion times sigma over 2. So there is a limit in probability of this. And the question, what is the limit? We know this limit exists, and we want to describe this limit. If we prove that the limit of this is equal to this integral, then we are done. Well, I will use the local time, asymptotics of local time, but now I would like to get this asymptotics of the local time. And now let me recall that a linear diffusion, this means continuous, strong Markov process, one-dimensional, can be obtained from a one-dimensional Brownian motion by two transformations: transformation of space and change of time. Well, and if you have a problem on a phase space 0 infinity, and if you can hit 0, then you can obtain linear diffusion on this with values on 0 infinity, also as application of two transformation, change of time and change of space, but you have to start not from Brownian motion, but from reflected Brownian motion. Well, there are some there should be some additional details that every point should be regular. So let me explain. Let us start with reflected Brownian motion. W reflected. This is a solution to Skorokhod problem. So we start from certain point, say x0, plus Brownian motion, plus the local time of this process at 0. So it is well known that reflected Brownian motion can be represented in this form. Now let me introduce the scale function. Of a Bessel process, of a square of a Bessel process of.
May I ask one?
Yes.
In the first equality, L0 is the local time of W reflected.
Yes, exactly.
Maybe 1/2.
Symmetric local time. Symmetric. So you divide by 2 epsilon, but you spent the time on the positive.
Okay.
Okay. Let me recall the scale function of a square of Bessel process X, and then I will also introduce the so-called speed measure. Okay, the scale function S of X, speed measure mdx, which is equal to, it has some density. And let me recall how to write speed measure and a scale for solution of a stochastic differential equation where coefficients are nice. So Lipschitz continuous, sigma is positive, diffusion coefficient is separated from 0. So in general case, if you have SDE of the form A of psi of t dt plus B of psi of t dw of t, then so-called scale function is any function such that its derivative is equal to exponent minus 2 integrals. So this point is arbitrary. So this lower limit is 0 or 1 or 2 or just some point. I will write here like star. From any point to x, and then a of z over b squared of z dz. And the speed measure is the following. One is 2 over s prime of x times b squared of x dx. So if we do formal calculation for process x of t, then we will see that s of x is equal to is equal to integral from 0 to x y to the power minus 2a over sigma squared dy, or so we can integrate and the result will be 1 minus 2a over sigma squared, or 1 minus 2a over sigma squared, and the speed measure is, so this density of the speed measure is 1 over sigma squared times x to the power 4a over sigma squared minus 1 if x is positive. Well, if x is positive. Well, if we consider a general diffusion where a and b are very, very nice functions, then it appears that psi of t can be represented as the following. S to the minus 1 is the inverse of the scale function. And then you take some Brownian motion. So let me write, say, some Brownian motion. And at the moment, tau of t. So this is so-called transformation of time. And what is tau of t? You consider the following additive functional integral from 0 to t rho of s minus first of Brownian motion of z dz, and then take its inverse. Tau of t is the inverse function. It is not 1 over phi. It is the inverse function. Function rho is positive, so this is increasing function. So if b is separated from 0, if a and b are Lipschitz continuous, then you may see that s prime is positive, so s is increasing, so inverse function exists. Phi of t is strictly increasing continuous function, so inverse function exists. So it was proved by, it seems to me, by Ito, or maybe Ito and Makin, that psi has the following representation. And by the way, if you have this representation, and if you know psi, then you can calculate b. And what is b? B of t is s of psi of t. So you take a scale of psi and then write here phi of t. So this is one-to-one. This is one-to-one transform between some Brownian motion and a solution to stochastic differential equation. Well, this is a classical theory, and there is some problem for this process, but it is not a very big problem. Okay, so let us do some transforms. Let us apply scale function to x, then transform the time, and you will see a representation. So we have s. Scale function is this. You can calculate these integrals and just forget about scale function and say, okay, let us consider function s of x. Let us consider inverse function. And I would like to recall you that a is less than sigma squared over 4 and greater than 0. So this parameter is less than 1/2. So if you consider inverse function, then you will have power function, but the power will be greater than 1/2. And if the power is greater than 1/2, then this function is twice continuously differentiable at 0, and 0 is bad point. So you may apply Ito formula for s minus 1 of x of t. And if you apply Ito formula, then you will get representation. And then you will get the following representation. So let me denote this process by V of t. And the answer is this. Representation is, it has the following. Okay, I'm sorry. Plus integral from 0 to t. Ah, no, excuse me. Excuse me. We consider the process so reflected Brownian motion. Yes, we consider we apply Ito formula for reflected Brownian motion. So assume that V of t is this of W reflected, and the answer is this. V0 plus integral from 0 to t V of z to the power 2a over sigma squared d b of z, this is a Brownian motion, plus integral from 0 to t 1 over sigma squared v of z raised to the power 4a over sigma squared minus 1 times a and dz, and there is no local time term, and the reason is the following. As this inverse function has the following form: x, well, some constant times x to the power 2 plus something positive, some, say, kappa. And when you apply Ito formula, then second derivative and first derivative at 0 is 0. That's why local times term disappears. So reflected Brownian motion has a local time in the stochastic differential equation, but not for V.
Excuse me, what is the process B? You said that this is another Brownian motion.
Oh, W, excuse me.
Because you mentioned it.
Okay, let me write here Brownian motion. I don't want to mix with this Wiener process. Just we say, well, let's consider reflected Brownian motion, which is a solution to this equation, and then take as inverse function of B.
Okay.
And we have this. And now we make transformation of time using this phi and using this inverse function. And you can represent, and here not B, but W reflected and W reflected. We use this W reflected. And well, theoretically, you may have a problem at 0. But if you write down, you know the Brownian motion has a local time at 0. You integrate a non-negative function of a reflected Brownian motion. And you can represent this integral as the integral with respect to local time of a Brownian motion. Maybe it is infinite. Well, theoretically, it might be infinite. But we know that this integral is equal to integral of rho of this inverse scale times y times local time of reflected Brownian motion, ty, dy. You can calculate this function explicitly. Yes, you have it seems to me it is infinity at 0. But L of ty, it is well known that this function is continuous in ty, and you have power asymptotics at 0, and this power is greater than -1/2. Oh, is greater than -1. So this function is integrable. So this functional is well defined, and inverse is well defined. And then you just make transformation of time and use just classical results on transformation of time in stochastic differential equations. And then you will see that after this change of time, the process you get satisfies stochastic differential equation of the, well, I forgot to write probably. No, I didn't. I don't. So when you do all of this, then you get the following result. Then that if you start from reflected Brownian motion, you make transformation of time, you make the transformation of scale, and you get some process. Then this process is a solution to stochastic differential equation of this form. Where W is some Wiener process. So another, it is not this B, but another Brownian motion. So dx tilde of t is a solution to sigma. Is a solution to equation dw tilde of t plus square root of x tilde of t here plus a dt.
Excuse me, how do you define this W with tilde?
So when you change a time,
Mm-hmm.
you will see here square root of a new process times so, well, W with tilde of t will be some transformation of so you'll have a continuous martingale with characteristic t.
Mm-hmm.
So W with tilde is some integral of this with change where, okay, this is probably integral from 0 to tau t. Yes,
Mm-hmm.
V of z to a over sigma squared dB of z. It seems to me this is the process, and maybe times sigma over 2 or times sigma.
No problem. I just asked because you mentioned, and usually it is so. Then we have a coefficients which can get 0. Then recovering of Brownian motion can be a problem. But now
But now we really don't.
Only problem in 0, and everything is good.
Yeah, and this problem is, well, is integrable. So actually,
Yeah.
there is no problems at all.
Okay.
Well, and as I told you, this transformation is one-to-one. So you can write that, you can see that this reflected Brownian motion is a transformation of x with tilde. So we take S of x with tilde and phi of t. And moreover, you can represent this function phi of t as a functional of this reflected Brownian motion, or, well, so let me write the formula. So this is the inverse function of tau, and it can be seen that tau of t is, well, okay. So this is the inverse of this. So if you make some changes of variables, then you will see that tau is equal to this. Well, we have representation phi as integral from 0 to t rho of w reflected of s of z dz, but you can make some transformations and you will see that you have this representation. And now you remember we had a process x and we had a linear process w. So let us apply this transformation and this transformation for this process x. And you will see that if x with tilde is a function of some reflected Brownian motion, then x also is a function of some reflected Brownian motion. So you can construct this Brownian motion from x, and vice versa. If you know that Brownian motion, then you can get x. And you know properties of a reflected Brownian motion of its local time. So the process x with tilde and the process x, they have same distribution. They also have a local time, and we will represent a local time of this process in terms of the local time of this reflected Brownian motion. Later on, I will not write tilde, and I will assume that our squared Bessel process has this representation with some Brownian motion. And now, what is the local time? We know that the local time of reflected Brownian motion satisfies the following property. For any non-negative measurable function f, the integral of f of reflected Brownian motion of z dz is equal to integral from 0 to infinity f of y times local time dy. Now, let us calculate integral of f of x of z dz. And we know that this square of Bessel process is a transformation of a reflected Brownian motion. So this point is tau of z dz. And now make a change of variables. So this is integral from 0 to, so tau of z is y. If z is between 0 and tau, then tau of z is between 0 and tau of t. F of s of minus 1 reflected Brownian motion of y d. Well, and what is z? Z is phi of the inverse function, phi of y d phi of y. And we remember what is phi. So let me write the answer. So we know what is S, we know what is rho, we make some transformations, and after some integration, oh, excuse me. So we write some transformation, we apply this formula for reflected Brownian motion, and finally we get that this integral is integral from 0 to infinity f of y times rho of y squared. Oh, excuse me. Well, and I can do everything with this process, even with process y. And we know that y of t is square root of x of t. So it would be simpler. So local time of reflected Brownian motion and the point phi of t, scale function of y squared, and then 2y s prime of y squared dy. So we see that this integral, if f is non-negative function, or if this integral makes sense, has the following representation: integral of f of y times something. So this is a local time of the process y of t y. Actually, this is just calculation, so nothing special. We never used some special structure of function rho and of function s. Well, square because y is square root of x. Well, we know that this local time is continuous in two arguments, time times and space. And we know that the local time of reflected Brownian motion is Hölder continuous in space variable with arbitrary parameter that is less than 1/2. So let me write 1/2 minus kappa, where kappa is any positive number. So, and then you remember that you know S, then that you have rho. So finally, you obtain the following result. So the local time of y at the point ty is equal to 2 over sigma squared y to the power 4a minus 1 over 4a over sigma squared minus 1 times local time of reflected Brownian motion at the point phi of t, scale function of y squared. So this is the answer. So this is the answer. And now let me return to principal value. So what was the principal value? The principal value is the integral of this form. And the function L small has this representation. So L small is the local time of the process y divided by this. And if we look at this formula, then we see that L small is this function, L T y. And we see that this function is continuous in Ty, and this function has a positive limit at 0. Moreover, it can be seen that this function is so that LTY minus LT0. So we use Hölder continuity of this local time, and it can be seen that this difference is less than or equal to some random constant, and then times 2y. And here 1 plus some positive number. And you can calculate this positive number explicitly using this a and sigma squared. So let me write just some new. So you have this asymptotic, and if you plug this asymptotic to the definition of principal value, you will see that this integral is well defined. Actually, it was not clear that this integral is well defined. Now we see that this integral is well defined. And the only thing is to prove that y have this representation. And actually, do you remember we applied Ito formula, and one moment. We applied Ito formula. No, it is not here. I wrote. I wrote this representation. So this term should converge to 1/2 times integral from 0 to infinity of that representation using that uses the local time y to a over sigma squared minus 2 times LTY minus LT0 d dy. And now we have two proofs. And what to do? And again, we use the definition of a local time. We know that you see, you have nice function. You have no zero at the denominator. So you can represent this integral as the integral that uses the local time. So let me do it. Let me do this. So let me just write the answer. So after all transformations, you see that okay, consider the first integral and let kappa be for a over sigma squared. When you integrate this, well, I'm sorry. Let me represent this. Let me make some transformation at first, and then you will see. So we have integral of a over square root x of s plus epsilon minus sigma squared over 4 x of s over x of s plus epsilon to the power 3 over 2 ds. Let me add and subtract epsilon. And when you add epsilon, you have x plus epsilon over x plus epsilon to the power 3 over 2. So you can say that this is integral of a minus sigma squared over 4 divided by square root and minus epsilon times minus plus sigma squared over 4 epsilon divided by x of s plus epsilon to the power 3/2 ds. And now represent this as integral of some function with respect to the local time. A minus sigma squared over 4 divided by square root plus this term, sigma squared over 4 times epsilon to the power, so let me write y squared plus epsilon, y squared plus epsilon, and times the local time of y at the point t and y. And then I use function L small. L small and times y to the power, let me check, to the power kappa minus 1, where kappa is 4a over sigma squared dy. And now I would like to pass to a limit as epsilon tends to 0 and to obtain somehow LT0. So let me consider. So after some transformations, we have two integrals. 1 minus kappa over square root of y squared plus epsilon, y to the power kappa minus 1 times this L small, and we subtract LT0 and we add LT0 and integrate with respect to y. And the same thing we do with the second integral. And the second integral is integral, well, epsilon y squared plus epsilon over 3/2 y to the power kappa minus 1. Again, LTY minus LT0 plus LT0 dy. And we want to pass to a limit as epsilon tends to 0. Let us start from the first integral, and the limit will be just integral of this. I use some asymptotics of this L small and Lebesgue theorem on Lebesgue dominated convergence theorem. So the limit of the first integral is just this. Now, consider limit of this. We have epsilon, and if y is positive, then this function converges to 0. Well, you have a problem at 0. This function y to the power k minus 2 and minus y squared and minus 3 is not integrable. But if you recall asymptotics of L at 0, then you will see that the function y to the power k minus 4 times LTY minus LT0 is integrable. So the limit of this integral is 0. So there is no this term in a limit. Now return to integrals. We have integral of, so let me erase this and this. We have to integrate these functions times LT0 over dy and this function times LT0 dy. And you see this function is independent of y. So you can move it outside the integral. And when you make calculations, then you see that this integral plus this integral is equal to 0. So this is a miracle. So it is not, so it is equal to 0, not converges to 0. No, it is just 0. It is just 0. Hence, the limit of certain additive functional, certain Riemann, or yes, certain Riemann integral is just integral. So is a principal value that I wrote. And this is all. So you see the proof, well, there are some technicalities when you calculate scale function, speed measure, but the first step is just represent squared Bessel process as a transformation of a reflected Brownian motion, and represent a reflected Brownian motion as certain transformation of a quadratic Bessel process. If you know a local time, properties of a local time for reflected Brownian motion, then you know properties of a local time for quadratic Bessel process and for Bessel process itself. And we are interested in asymptotics at 0, so we get it almost for free. Then we represent a Bessel process as a limit of square root of x of t plus epsilon. And we can apply Ito formula for this process. Just traditional Ito formula. We applied it, we get an additive Brownian motion, and we have some integral term. We represent this integral term in terms of local time, and then pass to a limit. Well, we have to add and to subtract the local time at 0. Well, L small, not the local time, but L small, T0. And the miracle is that additional term disappears. And this is just calculus, just calculations of integrals. It is impossible, well, it is impossible to calculate this integral, but it is possible to prove that this integral is equal to minus times this integral. And actually, this kappa depends on sigma and a, and you do all these calculations, and you get the result. Okay, that's all for today. Thank you.
Okay, thank you very much. And maybe somebody have questions or comments, please. Okay, then I have some questions. Firstly, I think that Engelbert did something devoted to representation of solution to SDE using local time, and especially studied behavior near the regular or irregular points of one-dimensional diffusions. So maybe it is related.
It is related, but this is not a case. Engelbert studied semi-martingales, solutions that are semi-martingales, and he has necessary and sufficient conditions for this.
Where he used, maybe he used semi-martingale local time, or what?
No. His process were semi-martingales. They were solutions to stochastic differential equations with Lebesgue integral with respect to ds. But my process is not a semi-martingale.
This is my second question. Maybe your process becomes to be non-semi-martingale or only due to the bad properties of this difference LTY minus LT0 with respect to t.
With respect to no, not with respect to y. With respect to y.
But let us. Can you just show us again the formula for the final statement? Okay. So we have martingale plus the integral, and here integral. We have and the dependence on t is only in the local time in this difference.
Without this integral is divergent.
Yes, it is good. It is good. Yes, I understand. But you see, when you have this difference, it can happen that it takes negative values or
yes, it may. Well, I cannot explain behavior at 0.
Yes.
When you discuss classical Skorokhod reflection, you have a term that pushes up. Yes. And here you have something strange.
Yes, exactly. Maybe we have such a situation. It is non-semi-martingale because it is sum of martingale and some function which has bad trajectories.
Yeah, very bad trajectories. Yes, very bad.
So we don't know anything about its behavior with respect to t or this last term, or know something.
Probably. I'm not sure. Maybe this process has, well, it is process of unbounded variation, but maybe it is, it has some variation of power greater than 1.
I see.
Finite variation of power greater than 1. Like Brownian motion has square variation. And this is maybe sometimes people consider process with so-called energy zero. So maybe this is the case.
That maybe you can consider some generalization instead of the martingale property. Okay, thank you.
Yeah, so you see, if you write here some indicator, for example, y greater than, say, epsilon, then this integral is equal to integral, yes, it's integral of y of s greater than epsilon, maybe some constant, ds over y of s.
So we have good process, yeah.
Yes. And if epsilon goes to 0, then, well, then this integral, and if you hit 0 before t, then this integral converges to infinity. Now, if you consider this integral, indicator y greater than epsilon, then this integral is just 0. Is 0. No. It is not 0. It is not 0. It increases only when the process hits 0.
Yes.
Hits 0. Yes. But when you pass to a limit, you have a difference of two processes. Both of them converges to infinity, and they compensate each other in some sense. And I cannot imagine, and I cannot explain in plain words what is the compensation, what is the behavior. Because outside of 0, you have just regular integral. Just you can calculate derivative. But when you hit 0, you have something strange.
I see. Interesting. Okay. Thank you again. And if there are no any other questions, then we finish our work for today. And maybe we can ask Georgi who will be the next speaker. Georgi, do you know? Georgi. Okay, then we will have an announcement. I hope. Okay. Okay. Thanks everybody. See you next week. Bye.
Goodbye.
Bye.
Bye.